Hi, everybody. This is Nicole Meyer, the Digital Strategy Manager for PHCP Pros. I just wanted to thank you all for joining us today, as well as Circuit Solver by ThermOmegaTech for sponsoring this webinar. What's the hype with thermostatic balancing valves? Attendees of this webinar can receive 0.1 ASPE CEUs for attending. For both live and on-demand attendees who would like to receive a certificate of completion, you must attend the entire presentation and click the I want a certificate of completion link in the handout section of your screen, and then submit your information. You will also be automatically taken to this link at the end of the presentation. Please also feel free to submit a question in the questions and answers box on your screen at any point throughout the presentation. All questions will be addressed at the end of the webinar. Now it is my pleasure to introduce today's speakers, Tom Ruggierio. Tom is the Director of Sales, Commercial Plumbing at ThermOmegaTech. He has over 35 years of experience in industrial automation, fluid power, and the plumbing HVAC industries. Tom has conducted dozens of webinars and has written several articles regarding designing and balancing domestic hot water systems. And with that, Tom, I will let you take it away.
Thanks, Nicole. Thanks for the warm introduction as well. As Nicole said, my name is Tom Ruggierio. I'm Director of Sales for Commercial Plumbing at ThermOmegaTech. Before we start on this presentation, I'd just like to give you a little bit of background why I put this together. For those of you out there not familiar with the technology, it's been around since the early 1900s, so for well over 100 years. It started off in the auto industry for controlling temperature in automobile engines. And it's kind of broadened its applications a lot over the years. Presently, it's used in aerospace and defense, in industrial applications, HVAC and hydronics, and in plumbing, which we're more interested about today. You'll see that in master mechanical mixing valves, point of use mixing valves, and more recently in thermostatic balancing valves. So over the last 10 years, thermostatic balancing valves have been on the market, and there's been thousands of successful installations. So 10 years ago, there was only one manufacturer of thermostatic balancing valves. But today, there's over a dozen. So because of all the activity going on, and I was just out at the ASPE Tech Symposium last month, and there was a number of presentations on domestic hot water systems. And basically, the consensus was that thermostatic balancing valves is definitely where everyone is going these days. So I just thought it would be really good to give an introduction to the technology and to the valves, and introduce it to those that haven't really been exposed to it before. So thank you. So the agenda, we're going to go very briefly over the history of balancing valves, the types of balancing valves, then go into why do we recirculate and balance domestic hot water systems, review manual, pressure independent, and electric balancing valves, and then get into the thermostatic portion of the presentation, where we're going to talk about thermostatic actuators, thermostatic balancing valves, how to select a return temperature, why do you need a dynamic balancing valve? And then we'll get into more technical discussions about the CV of valves and the differences between fixed and adjustable thermostatic balancing valves. That's the two types of thermostatic balancing valves that are on the market today. And then introduce a new product, a reverse acting thermostatic balancing valve. And then go over some FAQs and points to remember, and then we'll close it off with a question session. So the history of balancing valves, somewhere during the mid-50s, recirculating domestic hot water systems came into existence. So that's the best I could find using my new best friend, ChatGPT. So somewhere in the mid-50s, they started recirculating domestic hot water systems. It became more popular in the 60s and 70s when they were basically driving to water and energy conservation measures. Now today's systems are much more advanced with the advent of variable speed pumps, digital mixing valves, and electric and thermostatic balancing valves. 10 years ago, when thermostatic balancing valves first came on the market, very little people were using various variable speed pumps or digital mixing valves or, different components like that. But today they're all becoming more and more popular. So why do we recirculate? Well, the three basic reasons why we recirculate a domestic hot water system. One is occupant comfort. You basically, if you had a building and your water heater and the mechanical room was in the basement, and you were basically on the, say, fifth or sixth floor, and you were the first one to turn a shower on in the morning, overnight, all the water in the piping has cooled down, and now you have to basically turn on the shower and wait for all that cooled water to go down the drain before you start getting hot water again. So it's a lot of wasted water, and basically it kind of leads to a lot of occupant discomfort. So that's one of the main reasons why we recirculate the hot water. Now that we're recirculating the hot water, and the idea is to basically you turn on a fixture and the hot water is there instantaneously. The next point of the discussion is, why do you need to balance the domestic hot water system? So here we have a typical sketch of a domestic hot water system with 4 risers and no balancing. So we have our water heater, our mixing valve, and our pump, and then 4 risers going from right to left. So as we all know, water goes to the path of least resistance. So in this sketch here with no balancing, this first riser immediately to the left of the mixing valve has the path of least resistance, and it also has the least amount of heat loss because the piping is a lot less than it is in the other ones. So as you move from the right to the left, the resistance to flow increases and the heat loss increases because the length of the pipes are increasing. And so when you get out all the way out to the left here, you're getting basically very little flow, if any, and you have a high resistance to flow, and you basically have very high heat loss. So the water temperature here, if you turn on a fixture without balancing, would be very cold, if existent at all. So what you basically do then is we basically put balancing valves, in this case here, at the top of each one of these risers. And the idea is to normalize all of these risers such that they're all getting the flow they need in their particular branches to overcome the heat loss. So for this type of basic design, what would happen once you put balancing valves up there, and they could be any type of balancing valves. They could be manual balancing valves, pressure independent, or thermostatic, or electric. But the idea is, once they're set up, this first riser here, the one with the least resistance to flow and the lowest heat loss, is going to basically have the least amount of flow in it once the system is balanced. And as you go from right to left, the adjustable flow in each of these risers will increase, so that now the system would become normalized, and the one all the way to the left will have the most flow, so that it will overcome the heat loss and the high resistance to flow. So in theory, if the system is properly balanced, now they will all have the same temperatures. So that's the basic reason why we need to balance a system. So there are several types of balancing valves on the market. Manual, which I'm sure a majority of you, if not all of you, have been exposed to and probably are using and maybe still using, which is more of a ball valve type of a valve with pressure ports on there, which are used to basically determine the flow. The next one is fixed flow, which has several names: fixed flow, pressure independent, automatic. Basically, it's a valve that you place a cartridge in of a given flow rate, and regardless of the pressure drop, that valve will always produce the same flow rate through that branch or riser. Next is electric, which is still not that popular because of the high cost of using it, but it probably is the most effective as far as providing the best results. But that will consist of a temperature measurement device in there, a motor-driven valves, and controls. Typically, this type of valve will interface to a BMS system, building management system, or some type of a custom controller. Then last but not least is what we're talking about today, is thermostatic balancing valves. The thermostatic balancing valves, the flow is modulated by the water temperature. So this is directly addressing the issue of trying to control temperature. And there are 2 types of thermostatic balancing valves on the market: fixed temperature and adjustable. So here's just a little chart that basically shows you the different graphics of the different types of balancing valves. On the left here, we have the manual balancing valves, which you can notice those because they have pressure ports and a knob on them. So they're basically the manual valves that you measure the pressure across to try to determine the flow. And then to the right of that in the gray is the pressure independent balancing valves, which you notice these have no knobs, but they basically have a cartridge that goes in them. And this cartridge you select for different flow rates. It could be a half a GPM, 3/4 GPM, 1 GPM. Some manufacturers have more granularity than others as far as the different cartridge flow rates, but that's the second type of balancing valve. So the problems with manual balancing valves, which I'm sure a lot of you have experienced, is that number one, to balance the system, it takes labor and it's an iterative process. So let's say, for instance, you have 10 risers or branches in a domestic hot water system. As you go through balancing each one, setting the balancing valve to get the right temperature, and you go through all 10 of those, now you have to go back again because every time you adjust the flow in one valve, you're basically impacting the flow in all the other branches or risers. So basically what you do is just keep on going through this iteratively until you basically get them all at the right temperature. And this can take a significant amount of time, especially the more branches or risers you have, the more complex the system, the more difficult it is to get them manually adjusted. And then typically you need some kind of a specialist, a tab person or a certified plumber or something to do the manual adjustments, which of course can consume a lot of dollars. You need some equipment. That's no big deal. Some pressure gauges and maybe a thermometer or something like that. And then a lot of times, more often maybe that I'd like to believe that these systems are done without really doing mathematical calculations. And so basically somebody's maybe you hear examples of people holding on to the valve and basically grabbing it, and when they feel the temperature is right, then they feel that it's adjusted and they go into the next one. So it's not very exacting in that method of doing it. And then they're pressure dependent, the whole system. So when you have manual balancing valves, if for some reason the pressure in the system changes, all the flow rates change, which could impact the balancing. So the next type of valve, that what I call fixed flow or automatic or pressure independent, where you put a cartridge in there for a certain flow rate, they basically are used to maintain, again, a certain flow rate throughout the given branch or riser. And I haven't experienced this myself, but I've heard from engineers in Southern California, and I've also heard more recently from a contractor up in Calgary, Canada, that this type of device is prone to clogging in high mineral content situations. Again, I haven't experienced that or seen it. I just heard it from other people. The other thing is that these types of valves are dependent on calculations on a branch or riser basis. In other words, you need to select that cartridge based on what the heat loss is in that branch or riser. And so there's an additional set of calculations that have to be done. And they're not dynamic. They're not dynamic from the perspective of changing as conditions change. So we'll cover that in a future slide, but basically there are conditions that could change that would affect the balance, and this type of valve is always going to produce the flow that's in the cartridge. And then historically, a lot of these valves have come from the hydronics industry, and because of they're in hydronics and not in potable water systems like domestic hot water systems, a number of these valves over the years have not been NSF 61 certified. I have seen recently at least one manufacturer offering this valve with NSF 61 certification. So I would just caution you, if you're using these valves and you want to stay compliant, just to make sure that they are NSF 61 certified. They should be stamped on the valve with the agency that basically certified them. So again, if you want to be compliant, just make sure, and you're using these valves, just make sure that they are NSF 61 certified. And then the last two types of valves, on the left is the electric balancing valves, which you can see that are motorized, and then on the right are thermostatic balancing valves. So the electronic balancing valves, they do provide excellent control and flexibility. You can basically, they're basically going to a building management system, so you can have a lot of flexibility in how you want to change things and manage things. They're really good at, because they're providing feedback and things like that to the building management system, they're really good for data gathering. They're fully automatic, so basically they consist of some type of temperature sensing device, controls, and the valves are motor driven. They tend to be more expensive than all the other types of balancing valves because there's a lot of labor associated with these. You have to basically run wires for the motors and for the temperature sensing. So that can take a lot of labor. And then you need some type of a custom controller, like a building management system or something else to basically interface to these valves. And because of these valves having multiple components in them compared to the other valves we already discussed, statistically, I would say that they're probably less reliable. There's more things that can go wrong. There's wires that could fall off. There's motors that could jam up or whatever. So statistically, I would say they are probably the least reliable. So let's get into thermostatic balancing valves, which is what we're here to talk about. And first off, every thermostatic type of valve is centered around a thermostatic actuator. And typically they're paraffin wax. They could be some other type of material, but typically they're paraffin wax. So what this diagram shows here, we have two representations of a thermostatic actuator. The one at the top here, left in the blue, is basically the actuator, the paraffin wax, in a solid position. At the bottom here is the same actuator with the paraffin wax in a liquid position. So the way you get the largest stroke out of this type of actuator is going from a solid to a liquid. When you go from a solid to a liquid, you're getting the maximum change in the volume. And what happens as that volume increases with temperature, the wax starts pushing on a diaphragm, and that diaphragm extends a piston. So basically, the way these work is, as temperature increases, the wax starts going from a solid to a liquid, the volume starts expanding, and the piston starts extending. As the temperature cools down, the wax goes from a liquid back to a solid, and the volume starts compressing, and then the piston starts retracting. So this type of technology, again, has been around for well over 100 years. Freeze protection valves, which are somewhere in the area of 30 degrees Fahrenheit, and high temperature shutoff valves, which can be in excess of 240 degrees Fahrenheit, basically all use this same type of actuator with different wax formulations. So again, very reliable, very simple. There's no shelf life associated with the paraffin wax. It doesn't change its characteristics over time. So these things have been on, in plumbing, I know we always talk about, it's behind the wall and, what's the service life and things like that. But this type of technology has been used in applications that have been 30, 40 years on, and nothing has really changed as far as the characteristics of these actuators. So now the actuator basically goes into a valve. And so this video we're showing here on the right is a basic thermostatic balancing valve that's at a fixed temperature, not an adjustable temperature. And what you see here is what my yellow cursor is pointing to. Hopefully you can see my cursor. What that's pointing to is the paraffin wax actuator, the cup where the wax is basically stored. Now this video is sped up. It's showing the valve moving a lot quicker than it would in real life. But basically what you'll see here on the right where I'm pointing to is an orifice, and this here that you see extending into the orifice is the plug. So as temperature increases, as I showed in the other slide, the piston extends and it's pushing the plug into that orifice. Now these are designed with a mechanical stop. So regardless of what type of thermostatic balancing valve, whether it's fixed or adjustable, but they're designed with a mechanical stop so that the valve never fully closes. That's one of the first questions we get from engineers all the time. They're worried about if you get the temperature, the valve closes, and then you're basically deadheading the recirc pump or overheating it. It never happens. The valve always has enough bypass through there under any temperature conditions to make sure that there's enough flow back through the pump. So this valve, let's say, for example, let's put some numbers on it. Let's say this valve had a 120 degree Fahrenheit return temperature. So basically on a fixed valve, it has a 10 degree Fahrenheit span. So at 120 F, the valve is in that closed position, that bypass position. At 110 or less, which is a 10 degree span, the valve is in a full open position. So this valve will modulate open to closed over 10 degrees Fahrenheit. And it will continually do that. As conditions change in a building for whatever reason, where you may need higher flow to offset heat loss or less flow to offset heat loss, this valve will basically adjust its position accordingly. So what I always like to say, you may hear me say several more times in this presentation, is this is a temperature device solving a temperature problem. Unlike the manual balancing valve and the pressure independent valves, they're both flow devices which are trying to indirectly figure out what you need from a flow rate to basically offset the heat loss in the system. These are directly solving the problem because they're temperature devices. So thermostatic balancing valves are ideal for retrofit because they're automatically balancing, solving any existing hot water issues in older buildings. One of the things that you'll hear from a lot of project managers at mechanical, contractors is first thing out of their mouths is no callbacks. They appreciate the fact that you're saving labor on the initial balancing, but they really like the fact that there's no callbacks because that's just the big problem for them when they pull plumbers off a job and then they get a phone call because someone's not getting hot water and they have to go back and service it. And that's really one of the big reasons how the thermostatic balancing valve started having success. I used to call that desperation installations, basically. What would happen, there may be, and a lot of this started out with hotels or maybe dormitories or multifamily units, but that the building wasn't getting hot water. They tried everything. They tried balancing several times and it wasn't working. Then they would increase the mixing valve output temperature or increase the size of the pump or things like that, and they still weren't getting it. The bottom line was that the system wasn't balanced and they just couldn't get it balanced properly. So out of desperation, I guess they went on Google or somewhere and they searched balancing valves and they came up with thermostatic balancing valves. So we'd get a phone call saying, hey, we have this system. We're doing everything we can. We can't get it balanced. Do you think your thermostatic valves will work? We put them in. They have hot water in a couple hours. And next thing you know, there's a loyal contractor. And so I always say we started building success one installation at a time. So that was a big way that we, with thermostatic balancing valves got a lot of success early on, was basically solving balancing issues that no one else could solve. Thermostatic balancing valves also supports accurate system balancing and design because you put the system in there and you put the valve in there and it's going to react the way that you design it to act. If you're looking for a certain return temperature in your system, you're going to get that. You don't have to worry about are the balancing valves set correctly or anything like that. And you don't have to calculate the flow requirements on a branch by branch basis. Thermostatic balancing valves will adjust as long as you have the pump size properly for flow and head loss or head pressure. These valves will basically, on an individual branch or riser basis, will adjust their position to where they need to overcome the heat loss. So you don't have to worry as you would with a manual balancing valve or a pressure independent valve. You wouldn't have to know what do I need as far as a flow rate goes in each of these branches or risers in the system. The valves, as long as the pump again is sized properly, it will take care of itself. And these valves, as I already mentioned, they're always allowing some flow, some bypass. They're never fully closed. And again, for the second time now, these are temperature devices solving a temperature problem, not a flow device indirectly trying to solve a temperature problem. So as I said, they're dynamic, they're self-actuated, they don't require any existing or any external power as an electric balancing valve would. They're basically opening and closing based on the temperature of the fluid going through them. That's what causes the wax to melt and change its position. That they adjust to system demands as parameters change. You don't have to worry about something changing the system. Maybe they expanded the building, or maybe they shut off floors of a building or whatever, where the balancing would have to change. You don't have to worry about that with thermostatic balancing valves. So again, that installs the way that you as the engineer or designer design the system. Basically, what you have to do is, if it's a fixed temperature thermostatic valve, you basically have to select what return temperature you're looking for. If it's an adjustable thermostatic balancing valve, you have to adjust that valve to whatever return temperature you're looking for. So the other thing you have to worry about, in addition to selecting the right temperature, is then specify the size of the valve. And basically, you'll size the valve according to the size of the piping in the branch or riser. So if it's a 1/2-inch branch or riser, you use a 1/2-inch balancing valve. 3/4 inch, you'd use a 3/4 inch. So you just match the valve to the pipe size. I would say, and I'm sure you know this as well as I do, but over 90-something% of the applications are either 1/2-inch or 3/4 inch. And from a temperature standpoint, probably, it used to be 110, 120. Now we're seeing that kind of elevate over time, where it's gradually increasing. The recirc temperatures are increasing, and maybe you're seeing that, and maybe you have customers that are asking you to start recircing at higher temperatures. The nice thing about thermostatic balancing valves versus, again, manual or pressure independent is that they work really well with ECM type pumps. You have two dynamic devices. You have the thermostatic valve, which is basically opening and closing based on temperature. And then you have the ECM or variable speed pumps that have different types of controls associated with them. What is used for the most part with thermostatic balancing valves and these types of pumps is putting them generally in a constant pressure mode. So under a constant pressure mode, as I described the operation before of a thermostatic balancing valve, under a constant pressure mode, basically as the valves start getting satisfied, they start closing. As the valves start closing, you're going to start seeing an increase in pressure across the pump. When the pump is in a constant pressure mode, that will be the signal to the pump to start slowing down the RPMs of that pump to maintain a constant pressure. So it's really a great way. You can also do it. There's auto adapt modes. Some of these ECM pumps have auto adapt modes. Some of them you could set by trying to maintain a constant return temperature, things like that. But it seems like the predominant way of doing it is in a constant pressure mode. Not saying that the other ways won't work, but it seems like that seems to be the optimum way of doing it. So again, we all know that these pumps generally are not very large. So even though these are optimized for energy efficiency, doing it this way, you're not necessarily saving a lot of energy, at least on a building by building basis. Maybe if you start combining it with thousands of buildings, maybe the energy starts counting for something. What I like personally about interfacing a thermostatic valve with a variable speed pump is the fact that now you can basically oversize the pump and not have to worry about excessive flow velocity. Because what happens is, again, if you did oversize the pump and you start getting the higher pressure drops, you're going to basically start slowing down the RPMs of the pump. So I think that kind of takes away some concerns that you may have with excessive flow velocity. So I think it's really a great way to optimize not only the use of energy, but also to help with more easily sizing the pump. So this is an important slide from the standpoint of first-time users with thermostatic balancing valves. I used to always say early on, people would say, where do I put these thermostatic balancing valves? And I'd say, put them in the same location you put your manual balancing valves. But I stopped short there, and then I started to realize after seeing some issues is that people, engineers would typically, in a lot of cases, use manual balancing valves in other locations, not just the typical location at the end of a branch or riser before the return. But like for instance, here where I have this red circle and a line through it, I've seen cases where people would put a manual balancing valve at the output of a pump for the reason that they have that ability. If they needed to throttle down the flow of the pump because they felt maybe the pump was too large or something like that, they could just put a manual balancing valve there, leave it wide open, and then if they needed to throttle it down, they have the ability to do that. And then I've seen them in other locations in a recirc system for various reasons. The problem doing that with a thermostatic balancing valve is, as I kind of said multiple times, it's a temperature device. What will happen if, for instance, you put a thermostatic balancing valve at the output of a pump? As soon as that starts seeing that higher return temperature, what's going to happen? That valve will start shutting down. It's going to start basically limiting the flow out of the pump. So again, and I'm sure you'll be able to get a copy of this presentation, but it's really key to make sure you don't put thermostatic balancing valves in any of these locations that aren't a traditional location for a balancing valve. So this is an important point to keep in mind. And lastly, there's another application for a thermostatic balancing valve, and that is if you have a mechanical master mixing valve, and sometimes you're fighting with how much flow do I want back to the master mixing valve and how much do I want back to the water heater, because I don't want to have too much flow back to the water heater where I have temperature creep during the night when nobody's using it, and I have a master mixing valve which is always some flow going through it. Overnight the temperature could start creeping if you have too much flow back to the water heater. If you don't have enough flow back to the water heater, you basically then will have temperature droop. So the advantage of a thermostatic balancing valve in this application is it can adjust the flow of the water back to the water heater based on the return temperature, so that you have a better chance of mitigating either temperature creep or temperature droop. So it's another great application. It's not a traditional balancing application, but it's another great application for a thermostatic balancing valve in a domestic hot water system. So why do you need a dynamic balancing valve? Again, the manual balancing valves and the pressure independent are not dynamic. They're fixed. Once you set them, they're not changing. Well, there's a lot of reasons why you may need a dynamic balancing valve. And the brunt of it all is that if conditions change, the balancing is going to need to change. So one situation could be ambient temperature. If you're in the northeast part of the country or in the Midwest, and you have some risers basically maybe along the outer wall of a building, and maybe they're not that well insulated, in February, you could have temperatures of, say, 40 degrees in that chase supporting those risers, or you could have temperatures up to 90, 95 degrees. That's a big delta T as far as the ambient temperature goes, and that can have a significant impact on the balancing or the flow required to offset the heat loss. The other thing is building occupancy. When we came out of COVID and people started coming back to buildings to work, we started seeing issues or hearing of issues where they weren't getting hot water. And the reason being because the system was never balanced. When the occupancy was at 100%, there was lots of activity with the lavatories and things like that. So there was always pulling hot water into the system. So it really didn't need to be balanced because there was enough water being pulled into the branches or risers based on usage. But once people started coming back and you only had 20% occupancy versus 100% occupancy, now the usage was very low, and now you started seeing balancing issues. So another reason why you needed dynamic balancing. We've had situations, especially when I've seen some of the hotels where they did expansion, and now they basically would have to rebalance the whole system based on expansion. With thermostatic balancing valves, you don't have to worry about that. Once the system is balanced, they will all basically act independently of each other and adjust the flow where they need to offset the heat loss. And then there's also can be, again, building reduction. Especially now with a lot of people working remotely, You can have these commercial buildings and they may be shutting off certain floors because there's no occupancy. But the manual balancing valve, shutting off those floors changes the balancing of the whole system. With a thermostatic balancing valve, you don't have to worry about that. And then last but not least is those problems I'm sure a lot of you have come across is the building ends up being fabricated not as you designed it. In other words, there may have been an interference point and they had to run some extra piping around an obstruction, or maybe a contractor left off insulation at a certain area or things like that. And now you have to figure out why that system is not balanced or why your calculations didn't work out. With thermostatic balancing valves, you don't have to worry about that. Again, they will adjust their position where they need to offset the heat loss. So now once you've decided you want to use the thermostatic balancing valve, again, one of the main things is to select the return temperature. And I've seen different ways employed in how people select the return temperature. I would say the most prominent and the easiest one is if you know what the desired return temperature is. So if somebody says, I want 115 coming out of the fixture, then you would select or adjust the thermostatic balancing valve to 115. Now, that is assuming that there is no point of use mixing valves. If you're recirculating at, say, 140 degrees and you want 115 coming out, well, basically you're going to have a point of use mixing valve that knocks that 140 down to 115. And in that case, you would basically select a 140 set point for that system that you're recirculating at 140. The other way is basically determining the return temperature, based on the temperature of your mixing valve minus your delta T. So if your mixing valve is at 120 degrees Fahrenheit and you have a delta T in the system of 5 degrees Fahrenheit, then that set point would be 115. There are people who are basically setting the return temp equal to the mixing valve temp. We all know there's going to be heat loss in the branches or risers. The theory here is if you set those the same with each other, then you will basically have that valve generally be more open than closed because you're going to have the heat loss and the valve is going to be trying to maintain that temperature. So the valve is going to tend to be more open. And I think the thinking there is now if you have the valve more in an open position, there's more flexibility as far as motion on either side of that temperature. The potential downside of that is with a fixed balancing valve that has a 10-degree range of open to close, if you have heat loss approaching 10 degrees Fahrenheit or higher, that valve will be full open all the time. And if a majority of your valves are full open, then you're basically going to have issues with balancing because you're going to be producing a lot more flow than you need. The other problem with doing it this way is all these valves on average are going to tend to be more open. So if they tend to be more open, there's going to be more flow. If there's more flow, then it's going to be less energy efficient. So it's just something to consider. Again, I prefer selecting the temperature based on whatever return temperature you're looking for. So one of the things that seems to be coming up more and more with thermostatic balancing valves and with manual balancing valves is the CV of a valve. And I was surprised, but there are a number of engineers and designers out there that don't really know what CV is. And CV stands for flow coefficient. So it's a unitless parameter. There's nothing attached to it like inches or gallons per minute or degrees Fahrenheit. It's just basically a number. And the higher the number, the less resistance to flow. The lower the number, the more resistance to flow. So the lower the CV for a given flow rate, you're going to have a higher pressure drop. So these equations on the right here are all the same equations, just looking at a different variable. So if you need to determine GPM going through a valve, you would need to know that valve CV and the pressure drop of it. And so that GPM is the square root of the pressure drop times the CV. So an example here is, let's say you had a valve that had a CV of 1 and a GPM of 1. Looking at this equation here, 1 divided by 1 is 1. 1 squared is 1. So the pressure drop across that valve under those conditions would be 1 psi. Now let's say you took that same valve and basically now the CV for whatever reason is at 0.5. So the GPM of 1, a CV of 0.5, 1 divided by 0.5 is 2, 2 squared is 4. So you can see how the square function impacts the pressure drop. As the CV went in half, the pressure drop increased by a factor of 4. So that's something you need to pay attention to when you're selecting your valves. So the other issue is, what is the design CV? So the design flow coefficient is really a crucial parameter for evaluating and selecting the valves and flow control devices in fluid systems. So it basically allows the engineers to determine their flow capacity under standardized conditions. So to me, what I typically use for a domestic hot water system, I always select a design CV based on 5 degrees Fahrenheit below your return temperature. So if your return temperature is 120, I basically would say that your design CV should be 115. Now, the thing that I'm cautioning you here is with the adjustable thermostatic balancing valves, you'll see design CVs all over the place. Some of them will have them at 90 degrees Fahrenheit. Some of them will have them at 110. So they have them all over the place. So to be consistent and really to have the better performing system, you need to either look at the curves or the data presented by the manufacturer, or basically ask the manufacturer, what is your CV at 5 degrees Fahrenheit below your return temperature? So getting into the fixed versus the adjustable type of balancing valves out there, the fixed, you basically, again, it comes from the factory with a certain return temperature. It's not adjustable in the field. It basically, now, the actuators themselves can be changed out in the field. They can be changed out very quickly. But as they come from the factory, they are basically set for a given return temperature. So sometimes people say they are tamper-proof because they're not adjustable. These typically have a larger CV than the adjustables because they're basically going from fully extended to fully retracted over 10 degrees Fahrenheit, where the adjustables are generally designed with a lot larger temperature span of somewhere in the order of 50 degrees Fahrenheit. So you're getting a similar motion over 50 degrees that you were getting over 10 degrees with the fixed. So, and then they tend to have the adjustable at the design CV, they tend to have a lot lower CV, which can produce a lot higher pressure drop. And you just have to take that into account when you're sizing the head pressure of your pump. And then the other thing is with the adjustable is because they are adjustable, now you're depending on a human to basically put those temperatures where they need to be. And so that's one less control point. So if you have a building that has 100 thermostatic balancing valves in there, and now you're having hot water issues, one of the questions that you have with the adjustable that you don't have with the fixed is, what is, did everybody, was all those set at the exact same setting, or some set higher or lower than they should be? So it's one less control point you have in the system. So again, it's just that flexibility comes with a price, and it's just something you need to keep in mind. So here's some basic diagrams of the fixed and the adjustable. And this is very similar to the video that I showed you with the fixed. You basically have your housing, your actuator, your spring, and then there's a piston and then a component that takes that piston and makes it a plug. The adjustable has a lot of the same components to it, but it has additional components because it also allows you to basically adjust the position of the actuator. And by adjusting the position of the actuator, that in effect is adjusting your return temperature, your control point. And so the fixed operates, can't be adjusted, operates over a 10-degree span from open to close, and the adjustable operates over a 50-degree span. So the result of that, there's two curves shown here. The one on the left is the fixed, and this curve is basically a temperature stroke curve. So you can see for different temperature, the distance that the actuator is stroking here. And then you can see it on the right for the adjustable. So because the adjustable is over a wide span, you need to have a wide operating range. So, and the result of that is, if you look at the light gray and the dark gray here in this diagram, so this valve operates over a 10-degree span. So from 110 to 120, this valve will stroke from a little bit above 0.05 to 2.5. So a very large stroke, relatively speaking. For that same temperature range for the adjustable from 110 to 120, that valve is stroking from a little bit less than 0.15 to maybe 1.19, 0.18. So it's basically, this is giving you 4 times the stroke that this gives you for the same temperature change. So, and that results basically in a CV change that's a lot lower and would result in a lot higher pressure drop. Again, it's not the end of the world. It just means you have to take that more into consideration when you're designing your or specifying your pump. So just some rough classification of the attributes of the fixed versus the adjustable. The fixed is tamper-proof, so it prevents unqualified personnel from adjusting in the field, potentially causing overhaul balancing issues, and it has a single control point. So, you know, a lot of times you hear the expression, a facilities person has never met a knob he hasn't liked to turn, kind of a thing. So that's just something to keep in mind. With the adjustable, obviously they are adjustable. There are knobs on there that basically can be turned. They do have some type of locking mechanisms on them, but they can be relatively easily overridden. So, but the nice thing about the adjustables, especially with contractors like in wholesalers, is that now they don't have to order valves of all different temperatures and inventorying all these different temperatures. They basically can order one size valve, 1/2 inch, 3/4 inch, and basically when a call comes for these valves, the contractor can set them for whatever return temperature that they need for that application. So it also allows for manual tweaking in the field. So if something isn't exactly right, you can adjust it a little bit to help bring it in maybe to tighter tolerance if that's critical to you in the application. The fixed has been out in the market for over 10 years. The adjustables, who are kind of recently coming on the market, a lot of them have been in the last 2 or 3 years. Some have been out there as long as 5 years. So if that's important to you, the length of time, the number of installations out there, then fixed is basically has a lot more length of time out in the field. Sizes, they both come in multiple sizes. You have to look at each manufacturer and see what sizes are available. Again, probably over 90% of what is being used is a 1/2 inch to 3/4 inch. There are applications we're seeing more and more that are 1 inch, and also come across a lot of applications for dual systems. By dual system, I mean one that basically does a combination of heat and recirc hot water. So, and some of those end up being 2 inches. And then assemblies, all the not say all, but there are a number of manufacturers that have come with assemblies with shutoff valves or strainers or check valves or things like that built into them. And then the fixed has definitely a higher CV than the adjustable. Again, something just to keep in mind. So next, and I know we're running out of time, so I'm going to go through this really quick. There's also what we call a reverse acting thermostatic valve on the market, and that acts just the opposite of a direct acting, which is what we've been doing for hot water systems. These valves will close on cooling water, not close on warming water. So they're used in cold water systems. They're used for recirculating cold water systems. VHA in their 1061 directive strongly recommends recirculating the cold water. There's a number of systems out there now that are recirculating cold water in VA hospitals. It's also a great application for liquid-cooled data centers, balancing liquid-cooled data centers, and then refrigeration system balancing. So I'll go over those examples real quick. Cold water recirculation. Basically, the VA feels it's really good, and I think a lot of scientists feel it's really good to keep that water moving. When you have a stagnant line, it's an opportunity for not only Legionella, but other waterborne pathogens to grow in that stagnant line. It also, by having that water constantly moving, It basically ensures that the residual or free chlorine in the system is distributed evenly throughout the cold water system and not basically just be in certain locations. And it keeps the water temperature even throughout the system. You may have hot spots and things like that. By recirculating the cold water, you're basically going to keep the temperature even throughout the system. And then there's the VHA 1061 directive. So liquid cooled data centers, on the left is a server rack, and all these servers along here basically are have water flowing through them, liquid flowing through them, through a cold plate. And basically here you're balancing that whole rack to one temperature, which is the least expensive way to do it, but not the best way. A better way and more expensive is you basically have a thermostatic balancing valve, a cold water balancing valve at each server location. So now if you have one server that's running a lot hotter than another server, that will be individually balanced. So therefore you'll have tighter control over the whole system. And then next is refrigeration systems. So basically on the bottom here, we have 3 water-cooled condensing units, and then basically you have a pump that's flowing the coolant through all these systems, and you have balancing valves here. These could be manual balancing valves. They could be pressure independent balancing valves. They could be electric balancing valves. And then you have the evaporative fluid cooler, where basically you keep on cycling through this and it keeps on condensing and cooling off the water. So this could be like an example real quick could be, this could be in a grocery store, this could be a refrigerated unit which has like 3 doors to it. And you have the person in the center who just he opens the door to buy some ice cream and they can't determine what ice cream they want. And they're leaving that door wide open and all the hot air is getting in there and basically warming up the whole system. So with thermostatic balancing valves in this location, this is going to keep on adjusting the flow to what it has to make sure it keeps the system cool. So this is another application for it. So some of the frequently asked questions. Do thermostatic balancing valves completely shut? We already talked about that. No, they don't. They have a bypass in there. How do I size a pump for flow? We're not sure of the position of the valve. Sizing the pumps for heat loss has nothing to do with a thermostatic valve or any type of valve in there. It's based on the piping, the insulation, the size of the piping, and the length of the piping and the ambient temperature. So it has nothing to do with the balancing valve. So don't get concerned about where's the valve going to be position-wise when I have to size my pump. And then when you have to size the pump for head pressure, you're not sure of the position of the valve. You basically go to the design CV, which I said is 5 degrees less than your return temperature, and use that CV to determine for the given flow you need to offset the heat loss, what that pressure drop across the valve is. And that's how you would basically help you size the pump. Do I need to specify a variable speed pump when using thermostatic balancing valves? That's a big question I get a lot, and that is no, you don't, because 10 years ago, 97% of the applications had no adjustable variable speed pumps in there. Now today, that's a lot higher, but still, I would say out in the field, probably 80 to 85% at least of the installations are all fixed speed pumps. How do I specify the valve size? You match the line size. What is the maximum flow through the valve? You look at the maximum CV of the valve, you assume a pressure drop, and then basically you determine what the maximum flow is. What is the minimum flow? The minimum flow through a thermostatic valve can actually, in theory, be 0 because these valves are self-actuated. You can put a thermostatic valve in a cup of hot water as high as or higher than whatever your return temperature is in that valve, and it will close. If you put it in cold water, it will open. So there's no pressure drop across the valve. There's no flow through the valve, and it still operates, opens, and closes. What is the typical balancing time when using thermostatic balancing valves? Typically, system, they will basically balance in around 2 hours. I just had, about a month ago, a contractor call me up and was excited because his system balanced in 20 minutes. The whole system was probably about 30 balancing valves. So, some points to remember. By code, everything needs to be NSF 61 certified. Thermostatic balancing valves have been in use for over 10 years with thousands of successful installations in domestic hot water systems, so it's not cutting-edge technology. It automatically and continuously balances domestic hot water systems. It reduces installation and maintenance costs. It's sustainable. As conditions change, it will change to where it needs to be. It's really strongly being recognized as the go-to solution for balancing domestic hot water systems. It's dynamic. It changes as condition changes. Again, a system is typically balanced in less than 2 hours. It's a temperature device solving a temperature problem, not a flow device trying to solve a temperature problem. Contractors love it because of no callbacks. So with that, sorry I ran a little bit late, but I will close the presentation and open it up for any questions.
All right. Thank you, Tom, for that great presentation. For all attendees, there is still time to submit your questions, but it looks like we have received a few already, so I'll just go ahead and officially begin our Q&A session. Tom, the first question we have here for you. Do thermostatic balancing valves have any mounting orientation limitations?
So good question. No, they don't have any mounting limitations. Even the check valves and these, if you have an optional check valve, they actually are spring checks, so they do not require any specific mounting orientation.
Great. Our next question here. With manual balancing valves at each branch connection of HWR, we typically do a balancing station which has a ball valve upstream and downstream and a check valve downstream. Would you recommend the same with these thermostatic ones as well?
So generally speaking, thermostatic balancing valves are highly reliable. They're not prone to failure. But for servicing issues, there always could be an issue. So it would be good to have shut-off valves on either side of the balancing valve. And as far as the check valve goes, we did a little study a few years ago. And honestly, unofficially, 50% of the engineers use check valves and 50% don't use check valves. So I think it depends on a lot of other system requirements to determine whether you need a check valve or not.
Great. Next question. Do you need aquastats to energize the recirc pump, and where would you locate them?
So that's a good question. We get that a lot. I think there are codes, we're changing in some areas now, but that require aquastats. Thermostatic balancing valves don't require aquastats to work properly. And especially if you combine a thermostatic balancing valve with a variable speed pump, then that will slow down the flow to where it needs to be to overcome the heat loss. So I know there's a new standard out there. I think it's UPC 2024 now allows you to make aquastats optional for healthcare systems because there is that concern with Legionella. If you're shutting off your pump and turning it back on again, it can promote the growth of Legionella. So you don't need it to work properly, but if you need it by code, the thermostatic balance valves will still work fine if an aquastat is employed.
All right, our next question here. Do you sell a thermostatically balancing valve that works in reverse, a valve that works on chilled water piping to keep a piece of equipment cool?
So I assume this question was probably posed before I got to that in the presentation. We do have available what we call reverse acting or cold water thermostatic valves that work the opposite of direct acting. So they are closing on cooling water. So yes, they are available.
Great. Our next question. Are thermostatic balancing valves prone to clogging in hard water conditions?
So there are different thermostatic balancing valves out there that are made of different materials. The ones that are made of stainless steel are definitely highly resistant to any type of mineral buildup. But the other ones, depending on the metal makeup, the resistance to high mineral content water could be less. But the other thing to keep in mind with thermostatic balancing valves is they are basically in motion all the time. Not that they're going high speed, but they are constantly moving. So it's less opportunity for any minerals to build up on the valve because they are in motion. So I would say whether it's a stainless steel balancing valve or some other material, they are definitely more resistant to scaling than the other types of manual balancing valves or pressure independent balancing valves.
Perfect. We're getting to the end of the hour here, so I think we'll just take about 2 or 3 more questions. Next question, Tom, are there any issues having different return temps on the TBV based on the branch use, aka kitchens versus restrooms on the same system?
No, you just have to keep in mind that the whatever setting you make on those balancing valves, that's what it's going to control to. So I mean, we have seen systems where they will have a different balancing valve for in the kitchen for like a 140 return versus the primary recirc system that may be at 110 or 115 or something like that. That's fine.
Great. Okay, and I think this will be our last question here. In addition to optional check valve, what about a strainer upstream?
So I think that answer. What I always tell people is you make the same decision with a thermostatic balancing valve as you would with a manual balancing valve or a pressure independent. If the water quality is such that you feel you need a strainer, regardless of the type of balancing valve, then you continue to use it. If you haven't used a strainer in the past for systems, then you don't need it with a thermostatic balancing valve.
All right, great. Well, with that, I think we will close out our Q&A session here. Thank you, Tom, again for the great presentation in the Q&A session. I would also like to give one more thanks to Circuit Solver by ThermOmegaTech for sponsoring this webinar. And of course, thank you all for attending as well. As I mentioned earlier, for both live and on-demand attendees who would like to receive a certificate of completion, you must have attended the entire presentation. You must also click the I Want a Certificate of Completion link in the handout section of your screen, and then submit your information. You should also be automatically taken to this link at the end of the webinar. Please keep in mind that it may take a few business days to receive your certificate via email. All attendees will also receive an email from us with more information on how to access a recording of this webinar, as well as an optional survey where you can let us know your thoughts. I know in our Q&A box, we also did get a few requests to receive the presentation in a PDF, and we will reach out to you individually by email to send those as well. For any questions about anything, feel free to email me at Nicole, Nicole, at PHCPPros.com. If you are interested in attending more PHCP Pros webinars, you can find details on our 2023 library and what we have currently scheduled on phcppros.com/webcast. On our website, you can also subscribe to our e-newsletter so you never miss hearing about a webinar you may want to attend. Thanks again for joining us and have a great day.